This is Moser with your Introduction to Reaction Stoichiometry. So, in this video, you should learn to explain what a mole ratio is, where they come from, and how to use them. And by the time you're done, you should be able to use a chemical equation to derive a mole ratio. Now, what you need to know going in. You need to know how to write correct formulas, you need to know how to predict products, and you definitely need to know how to make a balanced chemical equation. If you don't know this, you can't do this. Let's get started. What is stoichiometry anyway? Well, you've actually already done stoichiometry, but what you've done so far is called composition stoichiometry. So it's just dealing with the mass relationships of elements in a compound. This is where you figure out how many moles of carbon are present in 100 grams of carbon, or how many moles of iron 3 oxide are present in 2.5 kilograms of iron 3 oxide. That kind of stuff. Well, now you're ready to take on reaction stoichiometry. And this is where the chemistry really seems real. Reaction stoichiometry looks at the mass relationships between the reactants and the products in chemical reactions. It's a tool that allows you to mathematically predict how much of one chemical you can make using another chemical, or how much of one chemical will be required to make a certain amount of a product. It allows you to do some pretty cool stuff. So let's get started. All of those neat prediction tools come in the form of course, math problems. And there are 4 basic types of reaction stoichiometry problems. Sometimes we have both a given and an unknown in moles. Sometimes we have a given in moles while the unknown is in mass, grams. Sometimes we have a given in mass with an unknown in moles, but most commonly, and really most importantly, are problems where both the given and the unknown are in mass. Because honestly, there is no mole balance. If you're working in the real world, you need to understand how many grams of something you're going to require or produce. Now, how do we solve any of these problems? I'm glad you asked. Da-da-da-da-da-da, with a mole ratio. This is the single most important tool that you have to solve any type of reaction stoichiometry problem. And all it is, are you ready, is a conversion factor. Just like you've used conversion factors to do metric conversions or any kind of other conversion, mole ratio serves as a conversion factor that relates the amount in moles of 2 substances which are both involved in a chemical reaction. So where do we get mole ratios? I'm glad you asked. Take this lovely chemical equation right here, would ya? We have 3 moles of potassium hydroxide reacting with 1 mole of hydrogen phosphate, otherwise known as phosphoric acid, to produce 1 mole of potassium phosphate and 3 moles of dihydrogen monoxide, in other words, water. So, the mole ratios are simply a ratio of how many moles of one chemical in the reaction will produce how many moles of another, or how many moles of one chemical in a reaction are required to fully react 1 mole of another. You know that ratios generally take the form of small whole numbers, 1 to 1, 2 to 1, 3 to 2, and mole ratios are no different. Though we don't usually write them that way, it's helpful to understand that they can be written that way. Now, let's make sure that we can get every single mole ratio that we need to out of this problem. I find it helpful to think back to FOIL, the technique for multiplying quantities and for multiplying polynomials in algebra. So, we can find a ratio between the first reactant and the first product. We can find a relationship, and let's write that down. So we know that the mole ratio between potassium hydroxide and potassium phosphate is 3 to 1. Now, the thing to keep in mind is that you can also flip that ratio on its head and say that the ratio of potassium phosphate to potassium hydroxide is 1 to 3. In that way, we get 2 mole ratios out of 1 relationship. Okay, so let's do the outside. So I'm showing that there are 3 moles of potassium hydroxide used for every 3 moles of water that are produced. Okay, I'm going to show that ratio is 3 to 3. It's tempting to simplify the ratio, but But I'm going to go ahead and leave it when we do the reaction stoichiometry. Though it's perfectly okay to simplify, I tend to leave them as is so that you can trace back where those numbers came from. Oh, which reminds me, where the heck did those numbers come from? Well, they came from the coefficients in front of our reactants and products. So we see that whatever those coefficients are, those generate our ratios. And note that I have flipped both of them both directions. Okay, let's finish up. So if we're thinking foil, of course we can also do inside. So that gives us our ratio between hydrogen phosphate and potassium phosphate. And that's pretty easy because it's 1 to 1, given that we have a sort of understood 1 as a coefficient in front of each of them. Now, if we were just foiling, we would do the lasts, and that would give us a ratio between hydrogen phosphate and water. That gives us a 1 to 3 ratio of hydrogen phosphate to water, or a 3 to 1 ratio of water to hydrogen phosphate. Now, again, as I said, if this was just algebra, we'd be done. But there's a difference here. When we're establishing mole ratios, we can also establish a mole ratio between the two products. This is a totally different thing than FOIL method, so this is where the analogy breaks down. Because what we can look at is how many moles of one reactant are required to fully react that many moles of the other reactant. And I may have just said product. If I did, scratch that. I meant reactant. Let's write the mole ratio for potassium hydroxide to hydrogen phosphate. That gives us a mole ratio for potassium phosphate to hydrogen, potassium hydroxide to hydrogen phosphate of 3 to 1, and hydrogen phosphate to potassium hydroxide of 1 to 3. But we're still not done. There's one more mole ratio we can write. We can actually write a mole ratio between the two products. So we can tell when we generate X number of moles of one product, how many moles of the other product will be produced. Let's write the mole ratio for potassium phosphate to water. Okay, so that gives us a ratio of potassium phosphate to water of 1 to 3, and water to potassium phosphate of 3 to 1. Boy, that's a whole lot of mole ratios to bring out of one little equation, isn't it? Yep. But that's all the equations, all of the mole ratios that we can get out of them. In your next video, what you'll do is use these mole ratios to solve reaction stoichiometry problems. Oh boy! See you later.